Mark Weitzman, and welcome back to Symmetry and Group Theory in Physics. In this fourth lesson, I want to resume our discussion of lower order groups by groups of order 6, which we'll find is equivalent to a permutation group on 3 objects. So the main thing I want to discuss in this lesson will be permutation groups, but I'll also try and fill in some more things that I might not have covered so far. And then we'll move on to group representations in the next lesson. So we left with the groups of order 5. Let's just look at groups of order 6. Remember, order means 6 elements. So if memory serves me right, I think there's 2 groups. As always, there's a cyclic group of order 6. And there's also the permutation group on 3 objects. And we'll always denote a permutation group by S, with the number of elements that are permuted. I'll discuss that in a second. And this group is also isomorphic to the dihedral group D3. I'm not going to go that much into dihedral groups, but first of all, let me explain what isomorphism is. If we have a group, let's say we call it simplest group, we can have EA and A squared equals E. And then somebody else comes along, so I got another group, EB, B squared equals E. Well, obviously the only difference between these 2 groups is the name. So if we made a mapping, let's say we mapped the identity to the identity, and we mapped A to B, what we would find would be that F of, let's say, a general element in this group, let's say G1, G2, is going to be equal to F of G1, F of G2. So this requirement, namely that we can compute the product here and then map it, or we can map and then compute the products, that it has to be the same. This is called homomorphism. And an isomorphism is simply a homomorphism that's one-to-one. But basically, when we say 2 groups are isomorphic, what we mean is they're the same group, they just have different names for their elements. So when I say S3 and the dihedral group are the same group, there's only one group, but they call them by 2 different names because there's a sequence of groups called like SN in general and DN, I guess. And these are not, in general, isomorphic. Only for 3 or 2. S2 is isomorphic to D2, I think. I'm not even sure that makes sense. Let me not do that. But S3 is isomorphic to D3. Now, rather than listing out the elements in the multiplication table and going through that A, B, C, D, E, F, and E, and all that stuff, we're going to start getting more physical on these groups. Probably should have done that earlier. So, in the case of a group of order 6, the easiest way to understand it is imagine you have an equilateral triangle in the plane. So here's the center. Let's call this 1, 2, 3. So what are the symmetries of this triangle? Well, there's 6 symmetries. I'm going to draw medians here. Okay. First thing we can do is nothing. Let's call that element E. E is the identity. If we don't do anything, we're got the same triangle. The second thing we could do is I could flip this triangle through this axis here. I could reflect 3 will go to 2, 2 will go to 3, and the triangle looks the same. So this is the set of elements in the group. I'm going to call that R1. That's reflection through the 1 axis. The axis that goes through 1. And likewise, I could reflect about this axis because it's an equilateral triangle. I could have R2, and I could have R3. Now, what other symmetries are there? Well, there's 2 other symmetries. I can rotate the triangle by 120 degrees about this point. If I do that, 1 will go to 2, 2 will go to 3, 3 will go to 1. So you can see that this physical viewpoint is basically the same as permuting these 3 values, 1, 2, 3. Anyway, I'm going to call that symmetry big R for rotation, and it's a rotation of 120 degrees. And then the last element, I can also rotate. There's 2 ways to look at this. I could rotate by minus 120 degrees, that's the same thing, or I could just rotate by 240 degrees. I'm going to avoid the negatives. I'm just going to call this R 4 pi over 3. So these are the 6 symmetries of an equilateral triangle in the plane. Rotations and translations. And each of these elements corresponds to what we call a permutation. So a permutation, let me work over here. Forget about the technical mathematics. It's just a reordering of the integers from 1 up to n. So if we're working with Sn, permutation on n objects, we can imagine labeling them 1, 2, 3, all the way up to n, and then we change them to some other order. This is set, so I don't want to use set. I'm going to use like an ordered pair, ordered n tuple. So this might go to 3, 7, 5, oops, it only goes up to n, 6, 1, 4, 2. So that's a permutation. Every integer goes to every other integer, and none are left out. It's 1 to 1. In many algebra books, they initially use this notation for permutations. We're not going to use it long, but in this case, 1 goes to 3, 2 goes to 6, 3 goes to 5, 4 goes to 1, 4 and 2. So you have to think of it, these are lined up in order, and then the permutation is 1 goes to 3, 2 goes to 6, 3 goes to 5, 4 goes to 1, 5 goes to 4, 6 goes to 2. This is a permutation on 6 objects. So, now, I said we're not going to use this notation because it turns out there's a much more convenient notation, which is called cycle notation, and I'll define that now. Cycle notation is, we start with an element, let's say 1, it goes to 3. And then we look at where 3 goes to. 3 goes to 5. And then we look where 5 goes to. 5 goes to 4. And then 4 goes to 1. Nope. 1 goes to 3, 3 goes to 5, 5 goes to 4, 4 goes to 1. Okay, yeah. Okay. So 4 goes back to 1, so we don't have to write again. So this is what we call a 4 cycle. And then we look at something that wasn't in this 4 cycle, like 2, and we say 2 goes to 6, and 6 goes to 2. So what you find and you prove is that any permutation can always be written as a product of cycles. Each cycle has a length that's maximum of n and minimum of 1. Oftentimes, if we had a permutation, let's say, we were to make this 1 goes to 1 and 4 goes to 3. Then the way we would write that is 2 goes to 6, 6 goes to 2, 3 goes to 5, 5 goes to 4, 4 goes to 1, no, 4 goes to 3. We already have 3 in there. And then we have 1 goes to 1. Usually we don't display the 1 cycles. It's just understood. If you don't see the number in here, it's the same. And the other thing about cycles that's nice is something like 1, 3, 5, 4. It's called a cycle. It's cyclic. So it's the same thing as 3, 5, 4, 1, which is equal to 5, 4, 1, 3. Don't reverse the directions though, because that's a different permutation. So what you can show is that every permutation can be written as disjoint cycles. There's no element in here that's also in here. Disjoint cycles. And what's good about it is, let me erase some of this stuff. It doesn't matter which order you write the cycles in. Because these things are disjoint, these cycles commute. So this is the notation we'll use for permutations, the cycle notation. It's very convenient and it will turn out to be very useful when discussing things like classes and everything. What I want to do is I want to rewrite the symmetries of the triangle in terms of permutations. So E does nothing. So E is a permutation. We just call it the identity permutation, or E. I think we don't really write it out as 1 cycle, 2 cycle, because they're all 1 cycles. Let's do R1. When we reflect about the 1 stays the same, but the 2 and 3 fix. So R1 is 2, 3. Now, let me give you some more terminology. A cycle, a 2 cycle, is a transposition. So you're just interchanging the 2 things, and all the other things in here don't change. Right now we're doing the permutation group on 3 objects. So we have 1, 2, 3. So R1 is the transposition 2, 3. R2, when we flip around this axis, it's the transposition 1, 3. I want to give you one more piece of terminology. Another thing you can prove fairly easily is that every permutation can be written as a product of transpositions. They may not be disjoint transpositions, but they can be written as a product of transpositions. And let me give you an example. Well, I'll give you an example in a second. Let me just do here quickly. R3, when we flip about 3, is 1, 2. Okay. Now, let's get to the By the way, the thing about group theory is just an infinite amount. I should say that the order of Sn is equal to n factorial. Right now we're doing S3, 3 factorial is 6, so we got 6 elements. This should be fairly obvious because you have n elements. The first element, 1, can map to n different integers. Okay, so that's n. So 1 can go, we have n possibilities. Then 2, once we choose that, we only have n minus 1 possibilities because we can't go to the same thing that 1 went to. So we have n minus 1. Then eventually we get down to n, which has 1. We take the product of all these things, it's just equal to n factorial. So S3 has 6 elements, S4 has 24 elements. One other fact I'm going to tell you right now, the reason why permutation groups are important is that it's also very easy to show that every group is isomorphic to a subgroup of a permutation group. So if you study everything about permutation groups and you know everything about permutation groups, then you really know everything about every group. This is not actually that useful, but it happens to be a fact. Permutation groups are important for a lot of reasons. Okay, let's get the R 2 pi over 3. So let's always take our rotations as counterclockwise. So when we rotate by 120, 1 goes to 2, 2 goes to 3, and 3 goes to 1. So this is what we call a 3 cycle. Now I said that every permutation can be written as a product of transpositions. Let me just show you in this case how that works. We can write this as, I hope, if I remember correctly, 1, 2, 2, 3. Excuse me. So let's see how this works. When you want to see how a permutation acts, remember it acts, we give it like an integer going in, and it goes this way. Just like in all the mathematics, functions operate to their right. So this is operating to the right, and then this one operates first, and then this one. So 1 is unaffected by this transposition. But then it hits this cycle, so 1 goes to 2, which is what we have here. 2 goes to 3 under this cycle. 3 is unaffected by this transposition, so 2 ends up going to 3, which is what we want. And 3 goes to 2, and then when it hits this, 2 goes to 1, so 3 ends up going to 1. So using these ideas of breaking 3 cycles into 2 cycles, and then 4 cycles into 3 cycles, and so on, you can show by induction that every permutation can be written as a product of transpositions. Now, one other thing I left out, an even permutation, P, can be written as a product of an even number of permutations, of an even number of transpositions. And an odd permutation is the same thing except an odd number of transpositions. So this permutation is even, it's written as 2 transpositions. These permutations are odd, and this permutation is even. And what you'll find is that the group Sn, half the elements are even, and half odd. And the even permutations, it will turn out, form a subgroup, An, and the order of An is equal to n factorial over 2. We might come across this, so just more terminology. Okay, I should have done this one too. R 4 pi over 3. Now when we rotate by 240, 1 goes to 3, and 3 goes to 2. and 2 goes to 1. And we can write this also as 1, 3, 3, 2. So you can see that they're a little bit different in how they end up writing. Now, I want to add a little more terminology. It will turn out that how you write a permutation in terms of cycles sort of determines what we call the class of that permutation. I'll define classes later, but all of these 3 permutations here are in a sense similar. They're in the same class. They're both a single transposition. The identity, again, it's in a class by itself. It's got no transpositions. And these 2 are in a are both product of 2 transpositions. They're also in their class. So it will turn out that S3 has 3 classes. This is one class, these 3 make another class, and then these 2 make a class. This will be important for group representations because it will turn out, this is something, you know, I'm not sure we'll prove it, but it will turn out that the number of irreducible representations of a group is equal to the number of classes of the group. So there'll be 3 representations of the 3 irreducible representations of the group S3. Okay, let me see what else. I just want to go. So I don't want to get into too much detail, but let me go back. Let me try and define classes. If we have an element G of the group, I want to define the class of G. I'm going to use this notation. And this is going to be equal to the set of all H inverse G H, where H is just an element of the group. So what we do is we take all the other group elements, and you notice this looks like a similarity transformation with respect to matrices. And basically that's what it is, because we're going to represent these group elements by matrices. So if we thought of these things as matrices, we would say this G, you know, if there's another element in this G, let's say we take one element, we get G prime, we would say G and G prime are equivalent. And now what we're going to do is we're going to put all equivalent elements in the same class. So you can, if you want, show that these 3 elements, if you multiply by, the identity case is always trivial, but if you multiply by another element in here on the left and its inverse on the right, or inverse on the left and the element on the right, you're going to get back in here. And same thing, if you multiply, let's do an example. Let's multiply, the inverse of 1, 2, 3 is just the opposite order. So let's do 3, 2, 1. And let's do 1, 3, R2. And let's do 1, 2, 3. Let's calculate what this permutation is. Okay, let's start. 1 goes to 2. 2, this does nothing on 2, then 2 goes to 1. So 1 goes to 1. I'll just write that down as a 1 cycle. 2 goes to 3. 3 goes to 1. And 1 goes to 3. So what we have is 2 going to 3. And 3 goes to 1. 1 goes to 3. And 3 goes to 1. No, that's not right. Let me do that again. 3 goes to 1, 1 goes to 3, and 3 goes to 2. So 3, 2. So this is equal to 2, 3. So that's basically what I said. When I multiply it by its inverse and then another element, I don't get the same element back, but I get an equivalent element in the class. So these are what's called conjugacy classes. And they're going to be very important when we do that. Now, what I haven't done is I haven't done the multiplication element for all these groups, but I do want to show one final thing. This group is non-commutative. Let's so let's do, I'm just going to take two, and we can see it's non-commutative. Let's say we do a reflection about the 2-axis, and this becomes 3, 1. And then if we reflect about the 3-axis, we now have 3 over here and 2 over there. So we end up having, that's too hard to see. Let me, let's just work it out. Let's just do 1, 2, 2, 2, 3. This is going to equal 1, 2, 3. Because 2 goes to 3, which is right. 3 goes to 2, and 2 goes to 1, which is right. And 1 goes to 2. But if we did it in the reversed order, 2, 3, and I'm going to write this. Instead of 2, 3, I'm going to write it as 3, 2, because it's the same. Doesn't matter cyclic order for cycles. And 2, 1. And this is going to be equal to 3, 2, 1. And these two permutations are different. So this group is our first group that's a non-abelian group. And we will find that there's 3 representations of this group. Two will be one-dimensional. There's a one-dimensional and a one-dimensional. Then there's a two-dimensional representation. And this is by matrices. And just to show you another general theorem, which we'll show later, it's interesting that 1 squared plus 1 squared plus 2 squared equals 6. We're going to find this is always the case. If we take the irreducible representations and take the dimensions and square them and add them up, they're always equal to the number of elements in the group. So with that, I'll come back next time and we'll do start doing group representations. And then once I've covered group representations, we can do some more theory. Then eventually I want to get back to the small oscillations and show you how this all fits in. I'll see you next time. Bye-bye.